Okay, in this class we discuss the implication of the quantization of the set component of orbital angular momentum, that is Lz is ml times h cross. Already we know that the magnitude of orbital angular momentum is quantized by this formula. Capital L is equal to root of L into L plus 1 h cross, where the small l is orbital quantum number. It has values 0, 1, 2 up to n minus 1, where n is principal quantum number. And ml has values minus L plus 1, etc. 0, 1, etc. up to plus L. Total 2L plus 1 values. Right? Yes. And this ml is called magnetic orbital quantum number. Now what is meant, so this equation talks about okay, this equation talks about the quantization of the magnitude of orbital angular momentum, right? So the magnitude of orbital angular momentum has quantized values. Now what is the meaning of this equation? What is the meaning of the quantization of z component of orbital angular momentum? Okay, let us try to illustrate this idea with some example. Then we will try to obtain a general idea about it. Suppose let us say we have an angular momentum state L equal to 1. We know that this is P state. Okay, so L equal to 1, which means ML has values minus 1, 0, plus 1, right? And what are the values for, so if small l equal to 1, what is capital L? Root of L into L plus 1 h cross, that is root 2 h cross. If ml has these values, what are the values of Lz? Lz is ml h cross, that is minus h cross, 0, plus h cross. What is meant by this? Okay, that is the question. Now, when okay, let us consider a semi-classical picturization here. According to the difference between quantum theory of hydrogen atom and Bohr atom model is that main difference or main difference with respect to the visualization is that in Bohr atom model or the Bohr atom model visualizes hydrogen atom that in such a way that the electron orbits around the nucleus around along some fixed orbits. In Bohr model it is circular orbit. In later Sommerfeld modified it as elliptical orbit. So whatever the shape, there is a fixed orbit around the nucleus for the electron. But in quantum model of hydrogen atom put forward by Schrödinger, there is no such fixed orbit. Electron wave just exists around the nucleus. There is no fixed orbit. So even if there is no fixed orbit, we can argue that electron being a charged particle, when it moves around the nucleus, because of the orbital motion, even though we cannot visualize it in a conventional sense, because of the orbital motion, when a charged particle moves in a closed path, then it produces a current loop, and this current loop acts as a magnetic dipole, or there is a magnetic dipole moment due to this orbital motion of the electron around the nucleus. Okay, so visualizing it is it's not possible, or whatever visualization we try to do, it will be partially erroneous. Okay, so we have to keep that in mind. Okay, so let us we can have this idea that electron is a charged particle. So When it moves around the nucleus, it produces, there is a current loop, and this current loop produces a magnetic dipole moment. So electron's orbital motion results in or produces some magnetic dipole moment. We can call it orbital magnetic dipole moment. Okay, so there is because of the orbital motion of the electron, orbital motion of electron leads to an orbital magnetic dipole moment. We know that any current loop produces a dipole moment. Here electron is a charged particle. When it moves in a closed path around the nucleus, there is some current loop. Okay, and this current loop produces a magnetic dipole moment. That is the idea. Now when you apply a magnetic field, this magnetic dipole moment interacts with the magnetic field. Okay, and so because of this interaction, okay, so the idea is that because of this interaction, this dipole moment will be oriented in certain specific ways about the field direction. Okay, so when you apply a magnetic field, this magnetic dipole moment interacts with the magnetic field, and it is oriented in certain specific directions with respect to the magnetic field. Okay, so let us see how we can talk about these directions. Let us see, first of all, what are these let me try to obtain an expression for this magnetic dipole moment. Again, this treatment is somewhat semi-classical, so let us try. We can say this magnetic dipole moment, let me use the symbol mu for that. This is equal to magnetic dipole moment due to any current loop is current into area. So I just assume that, again, let us for visualization, let us use the semi-classical model of Bohr. Let us argue that electron revolves around the nucleus in a circular path of radius r. Okay, this is the electron, something like this. So this current into area of the loop, area of the orbit, I can use this expression. Current is charged by time period, and area is pi r square. Okay, this is the magnetic dipole moment. We call it equation 1. And the orbital angular momentum of this electron is mvr, that is equal to m velocity is circumference by time period. That is in one time period it covers a distance of 2 pi r. So velocity is distance by time period into r. Okay, so we have m 2 pi by t into r square. Now let me take the ratio of these two. So magnetic dipole, orbital magnetic dipole moment divided by orbital angular momentum for the electron. Okay, so we have let us divide equation 1 by equation 2. Okay, so on the right side, what you have, pi r square will cancel, t will cancel, we have minus e by 2m. Okay, so this let us call it equation 3, and this is called gyromagnetic ratio or gyromagnetic ratio. Ratio between magnetic dipole moment and orbital angular momentum. Right? So if I cross multiply, I can write this as mu is equal to minus E by 2m into L. Right? Or vector mu is equal to minus E by 2m into vector I. So we can see that for the electron in the hydrogen atom, magnetic dipole moment, orbital magnetic dipole moment, and orbital angular momentum are in mutually opposite directions. Why? Because of the negative charge of the electron. Okay. So if we can think about it like this. Suppose we apply a magnetic field. Usually the direction of the magnetic field is taken as Z direction. Okay, so this is the direction of the magnetic field. Whatever be the direction of the applied magnetic field, we can take it as Z direction. That is only a convention. So suppose this is the direction of magnetic dipole moment mu, making an angle theta with the field direction. Then it means that the direction of magnetic orbital angular momentum will be exactly opposite. This is the idea. Okay, and this angle will be 180 minus theta, or this angle will be theta. Okay, so this electron, if in our semi-classical model, the electron's plane, orbital plane, will be something like this around the nucleus. According to right hand grip rule, if we look from the direction of this this direction, if we look from this direction, okay, if this is anti-clockwise rotation, then if you place your right hand in such a way that the fingers curl around this direction, then the thumb will be in the direction of in this direction, that is towards you. Okay, so if you look from here and the fingers are curling in this direction, that will be anti-clockwise direction. Then towards you will be the direction of the thumb, and this will be the direction of orbital angular momentum. So this will be the electron's plane of orbit around the nucleus. Again, remember that this is a semi-classical picture. Okay. So when you apply an external magnetic field, this magnetic dipole moment interacts with the magnetic field, and the atom will gain some potential energy. Okay, now the effect of this interaction is that this dipole moment will be oriented with respect to the field direction in certain particular angles or in particular orientations. Okay, that in other words, this theta will be having certain specific values or quantized values. Okay, this dipole moment will be oriented with respect to the field direction, not in all possible angles, but only in certain specific angles. What are these angles, or how do we specify these directions? Remember that if the dipole moment is oriented with respect to the field direction, then naturally this angular momentum will also be this orbital angular momentum will also be oriented, because orbital will be equally oriented, because orbital angular momentum direction is exactly opposite to the direction of the dipole moment. Okay, so if we say that the dipole moment will be oriented with respect to the field direction, we can equally well say that orbital angular momentum will be oriented with respect to the field direction in certain specific ways. Okay, now this idea is called space quantization. That is, the direction of orbital angular momentum is quantized. That is the meaning of space quantization. So, space quantization. means that um, orbital angular momentum vector can have only certain specific directions in space. How do these directions are decided? See, the point is that we even though this is the situation, orbital angular momentum can have only certain specific directions in space. We can to be able to measure it, to be able to observe it or measure it, we need some interaction. Okay, and this interaction is provided by an external magnetic field. So only when you apply an external magnetic field, what type of interaction is there? A magnetic interaction. Because of the orbital motion of the electron, we know that there is a dipole moment for the electron. This dipole moment will interact with the external field, and itself gets oriented with respect to the field direction. Then if the dipole moment is oriented with respect to the field direction, it's equivalently we can say that orbital angular momentum is oriented with respect to the field direction, and this orientation, this angle theta, can have only certain specific values. In other words, the z component of orbital angular momentum can have only certain specific values. What are these values? These values are given by this equation. Lz is equal to ml h cross. Okay, so let us come back to our example of small l equal to 1 and ml equal to minus L0 plus L, that is capital L is equal to root 2 h cross, and Lz has three different choices: minus h cross, 0 and plus h cross. Okay, so it means that when you apply in this case, that is in the case of p state, that is L small l equal to 1 means the angular momentum state is p state. For p state, the magnitude of orbital angular momentum is this much, and the direction of orbital angular momentum vector is such that the z component can have only three different choices. Okay, how do we measure it? By applying a magnetic field like this. Okay, and the magnetic field direction is specified as z direction. Let us see how do we draw the different directions of L vector L. Let me try like this. This is the z direction. Equivalently, that is field direction. Okay, then in order to draw this, one convention is we can draw a semicircle like this. This is to ensure that all the vectors are having the same length. Okay, now if I draw any vector, for example like this, the length of this vector represents the magnitude of orbital angular momentum. Okay, this vector represents orbital angular momentum, and the length of the vector is magnitude of orbital angular momentum. So remember, small l is equal to 1, which implies capital L is equal to root 2 h cross. Okay, so this is root 2 h cross, and small l equal to 1 means ml can have values minus 1, 0, plus 1, which implies Lz can have values minus h cross, 0, plus h cross. So this particular vector L, in order to get Lz, let us take this projection. Okay, here this Lz is equal to plus h cross. Then another possibility is this one. Again, capital L is equal to root 2 h cross. So this semicircle we are drawing because any vector will have the same length. Okay, now here what is the projection? If this is in the perpendicular to the z axis or in the xy plane, then the projection will be 0. That is, here Lz is equal to 0. Now consider this vector. Again, the length of the vector, that is capital L, is equal to root 2 h cross. This time the projection is negative. Lz is equal to minus h cross. So this is one convenient way of representing the three specific directions of angular momentum vector. And this idea is called space quantization. You can see that angular momentum vector cannot have all possible directions. It can have this direction such that projection is plus h cross. It can have this direction such that projection is 0, or it can have this direction such that projection is minus h cross. Okay, and let us consider more details. In fact, in this figure, we have shown only one particular direction, one particular vector with the projection plus h cross. But there can be other directions with projection plus h cross. Let me redraw this figure once again. This is a direction. Now, this time, earlier we considered this vector, right, with projection plus h cross. Consider with some particular angle. Consider another vector making the same angle with respect to z-axis and with the same length. Here also the projection is plus h cross. Okay, so you can consider a family of vectors which make the same angle with respect to z-axis, or you can imagine an ice cream cone like this, a circular cone like this, an ice cream cone like figure. All the vectors lying on this cone, consider these vectors, all of them make the same angle with respect to, consider this the circle, the base of the cone perpendicular to this plane. The base of this cone lies in the xy plane. So all these vectors on the ice cream cone, this circular cone, make the same angle with respect to z-axis. So if you take projection about the z-axis, okay, all these projections will be plus h cross. Okay, so this family of vectors lying on this cone, they will make all of them will be making projection with respect to z-axis or Lz value plus h cross. So the point is that the angular momentum vector can have a set of directions, a family of directions such that the projection is plus h cross. And what about the other two situations? Earlier in the first figure we have seen that this direction corresponds to Lz equal to 0. What about this direction? Lz equal to again 0. Now you can think about another family. Consider a circle like this, perpendicular to this z-axis. That means a circle lying in the xy plane. Okay, all the vectors on this circle, they are in the xy plane, and all of them will be having projection 0. So another family of directions, another set of directions such that projection about the z-axis or Lz equal to 0. And what about Lz equal to minus h cross? Earlier we considered only one vector, but there can be other vectors like this. There can be a family of vectors lying on this circular cone, an inverted circular cone, right? For example, vectors like this, on this circular cone, or for all of them the projection about the z-axis will be 0. Sorry, minus h cross. Projection about the z-axis will be minus h cross. So in fact these three choices, Lz equal to minus h cross, 0 and plus h cross, represents three family of directions. So one family of directions, one family of vectors lie on this circular cone corresponding to the projection plus h cross. Another family of vectors lie on the circle in the xy plane. So for all of them the projection Lz is equal to 0. And a third family lie on this inverted circular cone. For all of them the projection about the z-axis is minus h cross. Okay, so this but still these directions are quantized. Only these three set of directions are allowed. Okay, so this is the idea of space quantization. Vector, angular momentum vector can have only certain specific directions in space. This is called space quantization. Okay, and this can be measured when you apply a magnetic field, because you in order to observe this, in order to measure this, you need an external magnetic field, some direction which can be considered as the reference direction. And when you apply an external magnetic field, it is this magnetic dipole moment, orbital magnetic dipole moment, that interacts with the magnetic field. And there will be only certain specific orientations or directions. So this is the idea of space quantization. So when we say that LZ can have only certain specific directions, equivalently we can say that mu Z, the Z component of orbital magnetic dipole moment, can have only certain specific directions. Okay. Now there can be, what about the directions? What about LX? So LZ is quantized, right? What about LX and LY? What about LX and LY? That is the question. Yes. If we look at this figure, I said that, for example, I said that when we say ML equal to plus 1, okay, or LZ equal to plus H cross, there can be a family of directions such that LZ is equal to plus H cross, for a family of directions for L. Then what about the orbit of the electron? If we again try to visualize this orbit in terms of Bohr model, okay, what happens to this orbit? So you can try to visualize this orbit perpendicular to this angular momentum vector. For example, if there is an angular, you look at this first figure. If there is an angular momentum vector, consider this first figure. This figure. If there is an angular momentum vector along this direction with ML equal to or LZ equal to plus H cross, then okay, then you can visualize this orbit like this around it using the right hand grip rule. If L vector L is along this direction, okay, then perpendicular to that, using following the right hand grip rule, you will have this angular momentum vector. For this orbit, we can consider this orbit. For this direction of orbital angular momentum, for this horizontal direction, we can consider this orbit, and for the direction corresponding to minus H cross, the orbit will be something like this. So in this way, you can visualize an orbit perpendicular to the direction of orbital angular momentum vector. So when I say that there can be a family of directions like this, it means that there can be a family of you can think about the orbits like this. There will be an orbit like this, right? Okay, so these directions of these orbits can change in such a way that always the orbital angular momentum, the specific direction of orbital angular momentum vector will be lying on this cone in such a way that the projection is always plus H cross, right? Okay. So if you visualize the orbit, the orbital plane, the plane will be precessing or wobbling around the z-axis, precessing around the z-axis. This precession, if let us try to visualize this precession, it will be like the precession of the plane of a spinning top. Okay, if you imagine a spinning top, towards the end of its spin, when it begins to fall, then it's the plane of the top, the flat surface of the top will be wobbling or precessing around the z-axis, around the perpendicular axis. So electron's orbit you can similarly visualize as the angular momentum vector can be wobbling around the z-axis. always such that the z component is plus h cross. But when it processes about the z axis, it can have all possible values of x and y components. Okay, so Lx and Ly will not be quantized. They will be having all possible values, and the average values of Lx and Ly will be 0. Okay, so average value of Lx will be 0, and average value of Ly will be 0. And only Lz will have quantized values. Why average value of Lx is 0? Because Lx can have all possible values. It can have all possible values. This is more clearer, and similarly for Ly. This is clearer when we look at this family. This one for which Lz is equal to 0. So this orbit or this family of directions are lying on a circle on the xy plane. Okay, so these are the vectors showing the direction of the angular momentum vector. So perpendicular to this vector, you can imagine this electron's orbit, something like this. Okay, electron's orbits you can imagine around in this direction. So perpendicular to this one, using following the right circular right hand grip rule. Okay, so so here this orbital angular momentum vector is in the xy plane. So the plane of the orbit is in the yz plane, right? So it is actually it changes. It's not standing still in the yz plane. It changes. Okay, the angular momentum vector is in the xy plane. So this orbit will be perpendicular to that. Okay, so it changes in such a way that this angular momentum vector can have all possible directions lying on the circle. So in this precession, okay, x and y components can have all possible values. That is why the average value of Lx and Ly will be 0. Okay, this type of motion is called precession. Precession about the z axis. Okay, so this is a consequence of space quantization. Only one component of or in space quantization, only one component of angular momentum vector is quantized, and this component is conventionally named as z component. Okay, it's only a convention. The idea is that only one component is quantized. We choose that single quantized component as z component. That's all. The other two components are not quantized. They are continuously changing. They can have all possible values such that average value is 0. And the electron's orbit is precessing about the z axis such that the average value of Lx and Ly are 0, and only Lz can have quantized values. And there are two more points that we would like to understand. Let's try to underscore two more points regarding this space quantization. One point is that direction of orbital angular momentum vector can never be exactly parallel or anti-parallel to the field axis. And this field axis is often conventionally chosen as z axis. When I say field axis, what I mean is the axis of the magnetic field. So direction of angular momentum vector can never be exactly parallel or anti-parallel to the magnetic field axis. Why it is so? If this is so, if it is parallel or anti-parallel, then what happens? Suppose the direction of L is exactly parallel or anti-parallel to z axis. Okay, then what happens is magnitude of Lz will be equal to L. Okay, but what is the maximum value of magnitude of L? What is Lz maximum? Lz maximum is, we know Lz is equal to ml into h cross, and what is the maximum value of ml? Small l. Okay, then however, what is the value of L? Root of L into L plus 1 h cross. So this shows that Lz, magnitude of Lz is always less than L. Right? Maximum value of Lz can be only always less than, this is only L h cross, whereas the value of L is always root of L into L plus 1 h cross. So the maximum value of L will always, Lz will always be less than L. In our particular example, see, L is small l equal to 1, so capital L is equal to root 2 h cross. Root 2 is 1.414, right? And what are the values of Lz? Minus h cross, 0 and plus h cross. The maximum value is only h cross, plus or minus h cross, but that is less than the magnitude, h cross is less than root 2 h cross. This is so for any value of L and ml. So this means that Lz can never be equal to L, which means the plane or the direction of L can never be exactly parallel or anti-parallel to the field direction. Or if you talk in terms of electron's orbital plane, we can say that the electron's orbital plane can never be exactly on the xy plane, perpendicular to the z axis, perpendicular to the field axis. Okay, so that is one point. And a second point is electrons orbit cannot be confined to any single plane, any one plane, not necessarily on the xy plane. Earlier I said that it cannot be confined to xy plane, but let us now observe that it cannot be confined to any single plane. What does it mean? Suppose electron's orbit is confined to a single plane. Let us consider one plane like this. See, x-axis, y and z. Okay, suppose suppose electron's orbit is like this in the xz plane. Okay, perpendicular to y-axis. Right? Or let us say this is yz plane. Okay, on the surface of this board. X-axis is towards you, so that is easier to visualize. So let us say the electron's orbit is confined to the plane of this board, plane of this surface, on the which is yz plane, and x-axis is towards you. Okay, so that is the direction of the angular momentum vector. So if this is so, what is the situation now? What is Lx? Lx is equal to L, because the direction of the angular momentum vector is perpendicular to yz plane, that is along the x direction. So Lx is same as L. What is Ly? Lx is equal to L. So Ly is 0, Lz is 0. Electron's orbit is lying in the yz plane. So what it shows that all the three components are specified. All the three components have specified values, right? What is the problem with this? The problem is that now since the orbit is in the yz plane, right? What is delta x? What is the uncertainty in the x component of position? 0, because electron is completely revolving in the yz plane, so there is no x component of position. So delta px is equal to 0. Then according to uncertainty of uncertainty relationship between x and px, delta px tends to infinity. If delta x is 0, delta px is infinitely large. Okay, which means the x component of momentum is infinitely large, right? But this is not possible. This is not possible for a bound system. Remember, electron is bound to the nucleus in the hydrogen atom. Okay, so this is not possible for a bound system. So if whenever the electron, whenever we think that electron's orbit is confined to any single plane, okay, this problem always happens. Perpendicular to that plane, the uncertainty in position will be 0. So uncertainty in momentum tends to infinitely large, which is not allowed, which is not possible for any bound system. It means that electron's orbit cannot be confined to any single plane. And another point that we can notice is that whenever the electron's orbit is confined to a single plane, the component, the total angular momentum will be equal to the component perpendicular to that plane, naturally, because the angular momentum direction is always perpendicular to the plane of the orbit. Okay, so if it is confined to the yz plane, total angular momentum vector will be the value of the total angular momentum will be equal to Lx, the perpendicular component, and then the other two components are simply 0, Ly, and the components in the plane will be 0. Okay, so this can never have. So it means that when the orbit is confined to a plane, the three components are clearly specified. Okay, but what is the actual? So this is not possible according to uncertainty relationship. So what is the actual situation? Actual situation is that only one component of the electron, so electron's angular momentum, we usually conventionally choose it as that component. It has specific values, minus h cross 0, plus h cross, or in general ml h cross, right? The other two components, Lx and Ly, do not have any specific values. They can have all possible values. Okay, they can have all possible values from negative and positive values, so that the average value is 0. Okay, this is the idea. See, you should not confuse with this second idea, electron's orbit cannot be confined to any single plane, with the idea that um, the angular momentum vector is confined to a plane. For example, you look at here in the when projection Lz is equal to 0, I said that the angular momentum vector is confined to xy plane. But when the angular momentum vector is confined to xy plane, what about the plane of the orbit, electron's orbit? It can have different planes. I mean, perpendicular to, I mean, in the if angular momentum vector is in the xy plane, it can have different directions in the xy plane. So perpendicular to angular momentum vector, you can visualize electron's orbit. It can have different orientations, such that the angular momentum vector always lies in the xy plane. So the plane is not confined to, orbit is not confined to a single plane here. Only angular momentum vector is confined to a single plane. Okay, so this idea, second idea, electron's orbit cannot be confined to a single plane like this. This is stated in another way when we say that electron's orbit always precesses about the z-axis, because it cannot be confined to a single plane. It's always moving around the z-axis. The same idea can be expressed in another way. Any two components of angular momentum of the electron cannot have fixed values. Okay, see, the total angular momentum has a fixed value. For example, if L is equal to 1 here, then capital L total angular momentum is root 2 h cross. It has a fixed value. So this total angular momentum is, you can write it as root of Lx square plus Ly square plus Lz square. Okay, so one component of L, that is Lz, has again fixed values, minus h cross 0 and plus h cross in this case. But the other two components, Lx and Ly, do not have any fixed value. So if we have any fixed value for any two components besides Lz, suppose we have any fixed value for Lx, let us say. If Lx and Lz have fixed values, then since total angular momentum has a fixed value, root 2 h cross in this case, then Ly will also have a fixed value, square root of L square minus Lx square minus Ly square. Okay, so the idea is that if total angular momentum is quantized, magnitude of total angular momentum is quantized, and one component of angular momentum is also, orbital angular momentum, magnitude of orbital angular momentum is quantized. When I say total angular momentum, it may include spin also, but let us don't consider spin at this moment. So magnitude of orbital angular momentum is quantized, and one component of orbital angular momentum, Lz, is also quantized. That it's just one component. We are choosing that one component as Z component. The two components can never have quantized values. Two components of angular momentum can never have quantized values. In other words, they cannot be measured together in a state. Okay, another way of saying is that there cannot be any common eigenstate for these two operators. For the operators corresponding to any two components of angular momentum. Okay, another way of saying is that the operators corresponding to any two components of angular momentum, let us say Lx and Ly, they are non-commuting. They are non-commuting. If they are non-commuting, there cannot be a common eigenstate where they can be measured together. Okay, that means they cannot have definite values in a common state. That's the idea. This is not only for Lx and Ly. We can say Lx and Lz, okay, non-zero. Similarly, Ly and Lz also, they are non-commuting. Earlier we have seen their commutation rules. The commutation rules are like this: Lx Ly is equal to IH cross Lz. These are not Heisenberg commutation rules. They are different. Okay, they are not canonically conjugate variables. So the idea of these commutation rules is that they cannot be measured together. Two components of angular momentum can have definite values. They cannot be measured together in a common state. Only one component has a specific value, and that component we conventionally choose as Z component. So if Z component has specific value, then Lx and Ly are complete, and they can have any possible value from my negative value to positive value, so that their average value is 0. So physically it means that electrons orbit precesses around the z-axis. So you look at the precession of a spinning top around the vertical axis. It's just like that. The electron's plane will be precessing around the z-axis, or the angular momentum vector will be precessing around the z-axis. But this precession has a quantized nature. These precession directions are in such a way that their projections about the z-axis are quantized, and this is called space quantization. Okay, so let us conclude our discussion on space quantization.